Hello.
Morning.
Morning. So, how are you?
I'm okay. I'm pretty exhausted from just a whole lot of stuff happening this week. I forgot what I said Wednesday or Thursday about it, but just a lot of different things happening outside of like actual, life and schoolwork and stuff and work. So, but I'm okay. Thankfully, I'm you know on on track, but it's just a lot's been going on.
Yeah. 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 I imagine you've got you're just starting your classes and everything. So,
Yeah. How are you?
pretty good. Pretty good. I've been attending the BICA conference, which I'll talk about here. So, you wanted to do some updates, or you wanted to do you wanted to present some things?
Um, yeah, I don't really have any. I didn't get to write the CVMM 10 article that's kind of ever on my mind. Um, I will endeavor to do that, but I might talk a little bit about the ISPSM paper,
Okay.
um, but it's, it would be a pretty short discussion, just sort of like for feedback's sake or how I'm mapping things out. I kind of revised um, some of the points about it. So sort of like the plan of the paper is a little bit more constrained, um, which is good. So the program is ready for that event now. There's some email about that recently.
Yeah.
Um,
I mean, if you want to talk about the CBMM conference more formally, that would be good too. You don't need to have like a whole presentation about it.
yeah, I mean, I'm happy to talk. I will talk about it. I'm very interested in doing so. Um, but I want to also make like some kind of a I want to make some kind of a post about it because I feel like it's really significant.
Yeah.
Um, not I mean not as a MIT zealot or acolyte or fanboy about that. More like just who is there and the the vibe, if you will. The messages and the way the tone, excuse me, the way the tone is set or is being set for some other things. Yeah. Um, so yeah, I don't know. I don't know what order you'd like to go for things in, or who else will be here today. But
Well, I think I don't think Rashali will be here, but she will be giving us an update sometime next week on her final project. So we got an update from Raj last week in the open source meeting, which is great. Thank you, Raj. And now we're looking forward to Rashali's talk on VR for research, and so that's forthcoming. I don't know if Amanda will be here or Morgan, but we don't have to wait for them. And I want to do a shorter meeting today because I'm sort of in the middle of BICA, so no
yeah,
sessions right now. But um, yeah, just so why don't we talk about your things and yeah,
okay. I'll start with CBMM 10 just because that's um, ever present. Um, let me see the best thing I can easily share for that. 1 second. For those who don't know, I can do a general introduction of CBMM10 is related to MIT and its CBMM, or Center for Brains, Minds, and Machines. It's founded, it's the 10-year anniversary of it. It's part of a 10-year anniversary recap event. And it kind of was for those who aren't kind of up to date with MIT stuff, they now have something called, they now have something called, like the Quest, I think is their current branding, or like the Quest for Intelligence. But sort of the Quest is this new like macro unifying theme. Like they have the AI college and like like it's always, I think it's always interesting to take cues from people from groups.
Hello, Jesse. Are you there?
People like that.
You just dropped out
So,
for like about 30 seconds. Could you repeat what you were saying?
Yeah. What's up? I'm trying to get some of the pictures that I prepared before. Yeah, can you hear me?
Yes, I can hear you. Okay, yeah.
Yeah. Okay, I guess you can hear me now.
Yeah.
Can you hear me?
Yeah.
Anyway, let's proceed.
We lost Jesse. Hello, Morgan. How are you?
Well, I don't know if thank you. But I decided to just come back in now because it's a weird thing. Can you hear me now?
Yes.
Yeah, can you guys hear me?
Yes.
I can hear you, Morgan. You seem fine.
Oh, okay.
Bradley's
Sorry, I got the
just
cricket game
showing a
on.
little
Yeah.
weird. Yeah. I think there's a delay for Bradley, but I guess I'll just go on and try to go from there. Anyway, so I was doing a CBMM 10. Okay, they have this 10-year anniversary, and I was saying I think it's interesting to take away from some of these. I don't think MIT is sort of the only place doing anything interesting on this stuff, but I think it's interesting to go to these events that, especially when they combine industry and academia, and just see what things are there. And this structuring of the CBMM from 10 years ago was this attempt of bringing together the Venn diagram here of neuroscience as brains, minds as sort of the cognitive science, maybe psychology, maybe psychophysics was sort of mentioned there also, and then machines as sort of robots or neurotech or that thing, and that was sort of the thing at, the aim at the time. Um, and I'm kind of saying at the time in the sense because I I'm quite curious uh, regarding, say, like MIT's new branding is more the quest for intelligence and all that stuff, and and kind of the new discoveries in natural intelligence to produce the breakthrough in artificial intelligence. So it's still relevant. CVM's framing is still obviously relevant, and you're not going to throw away the CVM or anything. I'm not suggesting that, but more, I think like there were some pretty strong statements made, especially by the I don't know if I put it up on here, unfortunately. No, I didn't. Um, well, you can see. I'll try to get the one that actually shows the stuff, but this is Hinton Demise. Can never say his last name right. Um, and Illa or Ilya. Uh, this is the final panel, and the final panel was of yeah, here we go. Research on intelligence in the age of AI. On which problems should neuroscience, cognitive science, and computer science focus now? Do we need to understand the fundamental principles of learning, and in the sense of theoretical understanding like physics, and apply this understanding to the real nature of artificial systems? Um, and I would say honestly, I would say part of the answer is yes and also no, because that's obviously the rhetorical, like, yes, that's what it's about. And there was a strong pull, like there was a major conclusion from the panel saying, yes, we need new theories of learning, we need new theories of meta learning, we need new theories of, we do need that. But then it says, similar questions concern neuroscience and human intelligence from the society, industry, and science point of view, right? And this was Hasabi, Swinson, Verona, Siegel, Sestor, and Poggio. And one of the things that I guess the framing that this is kind of the slide that I'm going to reference most from the whole event. This Poggio made this slide and kind of presented it as, here's kind of, we need a science of intelligence, and we need we need work in this space. We need the theory work and getting for the fundamental common principles between natural and artificial intelligence. We need comparative study of intelligent behavior. And he, likens a lot towards cognitive science, psychophysics came up a few times there, and kind of comparative biology, kind of a little bit of dizzy, diverse intelligence stuff there, and then and recording inside the brains and from LLMs, recording from artificial systems to kind of track what each of the systems are doing, kind of how they're functioning, how they're going from the different states, how they're processing whatever, and looking for um, uh, the sort of recording what happened is analyzing it from that kind of more technical perspective, I guess. And what was interesting to me is that during this panel, there was there was some heavy, um, the voices were interesting to hear because there were a few voices that were very specific to, yes, we need a theory of learning. And there were a few voices that were kind of, um, I don't know, not to maybe overstate it. There were a few voices that were pretty disinterested in the role of human thought and human language, and I'll even say to some extent the human brain. And it was kind of interesting because I happened to be, um, I only really got to attend fully this panel and this panel. I did not get to attend the neuroscience one with DiCarlo as the chair and King Washer and Coach and the crew here. And I didn't it did not the first sort of the machines or robots panel with Bruce and these others here. Uh, it was kind of interesting because of all the other things that came up. I felt like um, you know, there was in terms of the embodiment talk, there was kind of this agnostic. I felt like it was interesting because I think, at least for myself, and I don't know if this is true or universal, for myself, if anything, I've heard more explicit in the past, and not from CBMM, so I should clarify that. But it almost felt like in the past for me, embodiment was a little more like, well, that's nice, or kind of dismissed.
Yeah.
And maybe it still is, but in the context of the last panel and in the context of the future of AI research, um, embodiment embodiment was sort of I don't know, like okay, like kind of agnostic. Like it wasn't turned away. It was just there. Like yeah, we might look at that.
Yeah.
Um, but compared to them, neuroscience and AI felt much much different. And I think the biggest surprise to me was this kind of I don't know. There was a definite sense that the brain is taking a backseat to me in the sense of I think I had a joke I had an exchange with something about this with Bradley in Slack somewhere, and it was something like, Bradley said like, oh well, the brain will never go out of style, and then I made like some Taylor Swift reference about the song Style. But it was sort of like it it wasn't the sense that the brain is obsolete, although I wonder to some extent. But it was more a yeah, the whole neuro AI stuff, and I'm really curious. I don't think I know we're talking about BICA and brain, brain inspired and cognitive architectures and so on and stuff like that, or biology and stuff like that. Um, I don't think there's going to be a drop off from that per se, but I think I started to see the future where AI, uh, like the summer and winter of neuro AI, maybe dipping into a winter of, or at least cooling a little bit. Um, and it's been interesting to kind of see people at the forefront of like all the LLM stuff and all of the other things and what they have to say about it. So yeah, there was people, somebody, and I forget who, explicitly said, yeah, I think neuro AI is crested. Some that was like explicit statement that was pretty unchallenged. Nobody challenged that and said, no, I don't think that's the case. Now I wasn't to say neuroscience isn't useful, but it was kind of a sense of, hey, neuroscience, you're useful in terms of analysis techniques, in terms of a lot of other things. There was definite statements like, yeah, like when fMRI came out, there were some new ideas and the new technique offered some things there, but there was kind of maybe a sense of challenging neuroscience also to be like, let's go with the theories, let's go with the better ideas, let's go with the better lines of inquiry, and not just sort of throwing existing assessments at just more and more and more data. And I think that harkens to what I've heard from a lot of different places about neuroscience. Isn't the trouble of neuroscience isn't the data. It's neuroscience may need some new ideas or just a new way of um, to bring thoughts or insights or work with a theory, work with analysis and so on. But there was a definite sense that yes, neuroscience can be helpful in terms of like analysis techniques and ways of differentiating, um, and ways of helping out with I'll go back to the diagram, ways of helping out with this stuff, like things that are gonna afford the differences and similarity, things that are gonna afford assessing and evaluating this stuff and being able to get compare the biological to the non-biological stuff, right? So I'm gonna pause there before I continue. I want to say a little bit more about the language of thought, and I want to say a little bit more about academia versus industry, because those are kind of the other main points as I round this up. But I want to pause there because I think some people might be delayed, so I'm going to pause for like 20 seconds if Bradley wants to say anything or anyone else does.
Yeah, so lots of interesting things here. This has a really strong sort of contrast with what's going on at BICA right now. So BICA has, they're kind of interested in biologically inspired architectures. So you'll see a lot of things that are, I don't know if they're necessarily biologically inspired, but they're definitely like cognitive models, which draw from cognition, cognitive science or cognitive psychology. Maybe less so from cognitive neuroscience, but the point is to use what they call cognitive architectures, which are basically taking like a neural network and instead of just saying we're going to use a neural network, using sort of more cognitive models of things. So you'd have a network, but it's assigned parts that are sort of cognitively salient. And so that's an interesting kind of conversation with respect to what's going on here. So yeah, they had a little bit of a discussion on some of the ways in which you can integrate biological systems and cognitive systems and all of that. So it's a nice parallel. I'll get into the BICA meeting later, but so yeah. Morgan, did you have anything you wanted to mention before we move on?
Oh yeah, I wasn't. There's a few other things I wanted to say before we're done. So
Oh yeah, yeah.
I know I think there's still a 20-second delay when you can hear stuff. So, but yes. Whoops. Where'd my thing go? I guess I should. Wait a second. It switched over here. Oh, okay. Now it's okay. Hold on. All right. Let me redo this. This screen. Take two ish.
Okay.
Cool. So you can still, yeah, all right. So the last 2 points I wanted to make were basically the language and thought stuff and kind of what happened with this panel and a few things from from here. I'll put this back over here. There's this, and then there's I think it was actually here. Yeah, my notes were here, and um, there was some interesting discussion about levels of creativity. There was definitely a sense of for Demis, there's a lot of deference to his opinions, and he gave some very very pointed commentary about sort of what should happen, like what should go down, and people were kind of he's a superstar in all of this in this whole research on AI stuff. So I mean, it's not a surprise in that, but it's a sense of he gave some very pointed feedback about a lot of things, and I'll get back to that pitch in a little bit. Yeah, I guess for right now, I will return to this image in the background and just say, um, for the language and thought panel, there was a place for it, but it was quite interesting because I happened to sit. Um, Oops, did I just lose my? I happened to sit. I happened to go to the panel, and the language thought panel was chaired by Josh Tenenbaum, and it was interesting because it was a little bit of you know it was sorry it was an interesting group of people. I'll show this here actually. This is the panel. Well, you can probably see it on my background image somewhat. But, yeah, it's funny because the panel was all this language is about LLMs and everything. And the panel was hardly about that. The panel was actually about a lot of talks. Like you have Gershman, who's a very brain big name in brain stuff from Harvard, was there, and development. Spelke and Tenenbaum were talking a lot, um, and 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 um, and so on. So I guess I'm trying to think what was my takeaway from the panel. Um, it was interesting because the panel honestly felt this panel felt like almost nothing to do with these LLMs. And I think it was interesting. There's a little bit of a rift between there. I feel like the the biggest tension in the entire event, it wasn't overt, but there was some tension between the language and thought panel and research on intelligence, because at least two, three, four times during this intelligence panel, there was a sense of, oh, I think we're over indexing on thought. There were definitely some you know some things that were kind of cognitively not elevated, I guess. Like Gary Marcus came up, and I think Hinton mentioned Marcus and kind of took a shot at him, saying, every time someone has said LLMs or AI can't do something, it comes around and it happens, and it's like, look at the collective work of Gary Marcus, something like that. And it wasn't necessarily outright antagonism, but whereas neuroscience kind of had this sort of well crested, um, but you're useful for your analytical tools. There really, I don't really interpret anything particularly positive said about cognitive science, um, or especially language. Noam Chomsky also got blown up a little bit. And I think, or was it in the language and thought panel? I forget. Let's see if I can find it quickly. Um, no, it was, yeah. So Hinton kind of had some beef with Marcus and Chomsky, but that's sort of, I don't think that it's that interesting or unusual. A lot of talk about benchmarks, a lot of talks about, I guess what I'll conclude on for this whole thing is some of the takeaways from the AI panel about what's ahead and what to do. Um, um, there there was some interesting discussion on terms of, like, even the even like embodiment kind of was, like I said, the embodiment machines were kind of agnostic, which is kind of interesting for me. And from someone who's like on the hardcore uh, cognitive science perspective that embraces embodiment fully, or embodiment plus, whatever you want to call it now, it'd be interesting because I think people from that camp would say, well, if you're kind of positive to neutral about embodiment, then you've got to understand that's related to all sorts of the cognitive stuff too. But that's, I didn't. Nobody said that. I didn't say there, and nobody that stuck around from the language and thought panel, or from what I could tell from the other panels, kind of, they weren't gonna, like, rush in to challenge it. But also, like, I don't I I'm having an interesting time just like how to couch this, because it's not like, it wasn't like this was a debate against the different groupings. It's just interesting for me to see what was said and what wasn't said. So I'll leave that part of that, and I'll conclude by saying, um, there's sort of talk about benchmarks. I guess I'll conclude by saying, the topics are, what's the difference between AI industry and then academia in terms of research? What about benchmarks and what about theories of learning? Um, there was the main thing. Let's go back to this. I'll put it. Yeah, the main thing. The main thing in somewhat concise terms, and this is like just total scrap notes that are undefined, obviously. But Dennis, and kind of representing this big AI from the industry's perspective, was saying, look, for academia, let yourself be agile, let yourself be focused on, like, more breadth versus depth, in the sense of, at least sort of, don't worry about competing with compute. Don't worry about the building largest models. Don't worry about the things that big AI is particularly in a resource and performance sense going to do. And they kind of said, you can. There's sort of this, you know, uh, a sense that, oh yeah, well, the big AI will lend you the resources if you can justify with your specific interests. But saying competing with that, maybe you don't need to do that. It's like, don't worry about that. Oh, what they really need is the theory work. I call it these days theory work, like neuroscience, like psychophysics, practical experiments. How are they going to wrestle these questions of emerging properties, testing benchmarks? How are we going to do that? We need new theories, explicitly saying we need new theories, new meta theories of learning. And it's going to be a really, really rich space for the next 10 years. And so it was, it wasn't like a, here's your order, do this. But there was a definite sense of, well, if I, if the titans and the persons at the top of the industrial AI thing we're saying what to focus on for the next 5 to 10 years, it's that theories of learning, especially in academia, especially people who aren't in the big tech companies. Because big tech, there was discussion about, big tech to some extent will likely be, focusing a lot on performance, on uh, speed and power and these like making these behemoth models and getting the resources to actually do it and saying, you don't need to compete with that per se, but find ways where we can do it. And there were a few questions from the crowd saying, "Hey, I want to do this. I want to. I want to. What's the best way for me to do this?" And basically, then they said again, like, "Well, do this stuff and talk to us, and we can see about getting you allocating resources for you to use for research purposes in academia, and use the flexibility of academia to the advantage of doing that. Don't try to cram, it really highlighting, okay, industry is better for this and academia is better for this, which is, I think, not their controversial statement, but kind of just the clarity about what can happen and where AI is going that way was quite interesting to me. And I think I will. My final remark will be: it's so interesting for me whenever I see like Josh Tenenbaum and the cognitive science people, and I'd be really curious. I think Gershman, didn't stick around for the whole panel back here. There's quite a bit of a lunch break, so um, but I kind of be curious. I wish I could do it. Maybe I will informally follow up with much of the panelists from here or even other ones and say, like, well, what's your take on that? Because I always get a sense that Tenenbaum is to play this sort of as the MIT guy, as the figurehead for the language and thought or the cognitive science stuff. Like he has to kind of play diplomat because all the hype right now is on, like, I would say almost post neuro inspired AI. Not in the sense that it's not biologically tied to anymore, but just sort of there's a lot of maybe slight condescension about the use of it again. Like it's a great time to be um I don't want to say connectionist, but a great time to be it's sort of like I think there was sort of like I'll stop sharing my screen here and say where did it go? Okay. It's an interesting time to be um it's an interesting time to be a there was sort of the deep. I look like I'm attempting to pop the door here. That's pretty.
Yeah.
There was um, like the deep learning hype train. Like when I went to my first conference in like 2017, 16, I think the deep learning was either peaking or cresting because it in some aspect of there's a lot of skepticism of is deep learning going to save us, and some people was like, yeah, it's not going to deep learning isn't going to save us. And so I think there was sort of maybe a little cresting around that time, and then other things happened. But now we're heavily into the LLM, hype era, and even with the pausing AI and all the letter stuff, there's a lot of stuff. And so I don't really I'm not trying to make too much in the sense of like gossip or whatever else. And like, oh, did you hear that this person said this at the MIT conference? It's much more, I think, in terms of like when you're trying to sort out the different kind of funding that you have and how you're making your pitches and stuff like that. I think that's kind of what comes to my mind more so in the sense of what are people saying, how do you have to present yourself to seem relevant, and how do you do this sort of diplomatic work of okay, I'm dancing to the tune that the big AI stuff right now is doing, but in the context of that, yes, I'm doing neuroscience research that's leaning towards a useful theory of intelligence. I'm doing cognitive science or psychophysics or psychology or whatever research that's going to help towards theory of learning, towards comparative stuff. I feel like the chart, the Poggio graph will kind of be a way for people to frame some of the research in academia going ahead. So, the end. Any questions?
Yeah, so I had a couple questions or a couple points. So I would like for you to pull up your Notion file again, or the screen share for the Notion file.
Yeah.
All right, yeah.
That's not. Okay. There we go. Okay. Which thing you looking for?
The Notion file, like where your notes were. There we go. Yeah. So I had a question. First of all, there was
Yeah,
this. Oh,
which part of the Notion?
it would probably be like where they were. Well, first of all, they were talking about scientific revolutions. I saw when you were kind of going through it. They were talking about AlphaFold and the scientific revolutions that it might enable.
Okay. I will look for the scientific revolutions bit.
Okay, so that's the one I wanted to talk about. So this is kind of interesting. They're kind of arguing almost like for a sort of a philosophy of science based on like a piece of technology here. It's like AlphaFold can enable, discovery. It can enable like the analysis of data sets, and it can actually create scientific models because it has some intuition about the data that it's putting out there for people, and that is, I guess, maybe a new philosophy of science. We talk about falsification and we talk about scientific revolutions and that, and this is kind of like a third category, which is almost like an intuition of data. And it's not like people haven't done this before. I mean, people used to do this all the time, or people have done this all the time. I mean, a lot of times mathematical equations are the way they are because people have to have an intuition about like how things work, mechanisms. And then you can write down a symbolic statement that sort of summarizes, um, what's going on there. And that goes back to like some of uh, the programs like Eureka, which were developed years ago, where they would try to discover physical laws from different types of physics data. Like they'd have a pendulum and they'd swing it, what they call a two-part pendulum, where it would like swing around, and you get one pendulum swinging and then the next pendulum swinging more, and you get these interesting dynamical trajectories, and then you can describe them using equations. But you have to have the system has to have some intuition of the data, some way to summarize it and put it into a symbolic statement. So I think that's kind of an interesting thing to follow up on. I've heard other people talk about this. That's why I'm talking about it, or that's why I'm interested in it. But definitely, yeah. Michael Nielsen, I think, has talked about it, where he's kind of thought about AlphaFold as being this sort of intuition of the data, but I don't know if he's actually written a paper on it. I'll have to look and see. So yeah, this is great. This is like this other thing is where we have to create the hypothesis, but we get this sort of primed uh, intuition machine.
There was an interesting discussion, and I hope I'm not. It just dropped out for me.
Oh, I'm still here.
So I don't know if
It's a delay.
Okay, I I think I'll just make a point. Um, there was some interesting discussions about okay, interesting discussions about um, there was a comment about data without theory, and it kind of I think in a way the AlphaFold comment and enable AI science and stuff here that we just mentioned was almost a response to it, or it happened. I think it was I think it was a response to this. Um, but how like the dangers of doing stuff without much theory, uh, and I don't remember kind of the punchline to it, but there was commentary about the theory required. If you don't have when you don't have a theory and you're just sort of arbitrarily like evaluating or processing the data, there's certain challenges to that too, and strengths and weaknesses to different types and amounts of theory or whatnot. But there was a pretty decent push for like why theory matters, if that makes sense. And like I think I think the new banner for CBM might be, and maybe it's what the I don't know, maybe it's what the quest for intelligence is anyway. Like the theory, uh, approach intelligence as a single grand challenges, et cetera, et cetera, et cetera. Um, and this from their website here. Scientific theories of natural intelligence must be developed. Computational models must be created, and these models must be compared against the capabilities and neuromechanisms of intelligence to assess real world problems. Which is basically this slide. Like this slide. I don't know if this slide is literally part of the question vision somewhere else, or Poe just reproducing the slide. It wasn't talked about that way, or at least the other participants didn't recognize it as such. Like, oh yeah, that's the quest slide. There's none of that. But there's obviously obvious overlaps for that. So cool. But I guess what I'll say is my 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 final point for all this, and maybe a nod to the BICA crowd, will be my rhetorical and trademark registered tagline will be intelligent is not um, I haven't quite worked it out yet, but intelligence is not the same thing as living or being alive. Um, or is it? Or is it? I guess is something to say, but sort of like differentiating. There's a lot of focus on a certain kind of intelligence, and I think the cognitive and the embodiment people, and even the robotics people, um, you know, I don't think the 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 winters and the summers are here, but I don't think they're out of the picture yet entirely. So that's my. I'll leave it at that for now. We took a lot of time on this, so that was fun, but also I think I'll just let you go on the rest of the meeting. So,
Oh no, I think this is great. Thank you. This is very good, and I enjoyed this recap because I think it brings up like almost like a the perspective that we need on what people are thinking. So I mean, we've talked about building roadmaps for our developmental AI, what we would call in house our initiatives, and I think this kind of gives me an idea, gives all of us an idea of what you know people are thinking in terms of approaches. That being said, that doesn't mean that that's the definitive way to do it. That's just the way that they do it at MIT. And noticing that their whole panel is from like MIT or Harvard is kind of like a. And we'll see with the BICA stuff that the world is a lot bigger than that. So, but yeah, it's some good. There are some good things there, and I think some of the trends are. I'm not quite sure that NeuroAI is crested.
I think yeah,
Yeah,
exactly. That's,
but yeah, I don't know. I mean, there are a lot of things that people are doing that there's more biological inspiration.
I
Remember,
would like to see. I would love to have seen a stronger rebuttal of NeuroAI question.
yeah, I don't exactly know what it is that like I don't know what they're trying to get out of neuroscience or biology. It'd be interesting to really kind of pinpoint that because people say something is, well, I tried it and it didn't work. What did you try? And then it's like, well, so it's kind of one of those things where the kind of the thing about like how you're integrating disciplines, but you're integrating them in a certain way, that maybe serves like a traditional view of AI, whereas maybe in another view of AI, or trying things fundamentally different than what's been done in the past is maybe more needed. Oh yeah, it was disappointing Richard Sutton's bitter lesson was not more explicitly referenced, but it was sure danced around a lot. Yeah, there's some there. Yeah, it's like you don't want to be too negative, or I don't know. But no, I think it's, yeah. Okay, yeah, that's good.
Yeah.
Okay. I think that's all I had in terms of questions. They did mention one thing about synergies. Is that like synergizing between neuroscience and cognitive science, or are they talking about like? I know we talk about synergies in our groups. So
Can you say more about that?
well, I mean, I didn't know what they said. You had in your notes something about, or they had in the program I saw, is one of the sessions they said synergies. Yeah, I don't know. It didn't really say any more than that. Maybe they weren't meant like synergies between different ideas. I don't know if they're on that train or not. The train of sort of dynamical systems and ecological
Yeah,
psychology and all that.
I see what you're saying here, and I really don't know. Um, I'm seeing at the time it said here, and it doesn't really like. I guess they mean the CBMM synergies, Venn diagram stuff.
Oh, okay.
It's synergies with AI. Like, okay,
Oh,
key open
yeah.
question synergies. I wonder what this. I wonder what this. I didn't go to this panel, and I really wonder if that meant. I felt like is this the same thing as like the key open question for this panel was LLMs. What's missing? Blah blah LLM. And it's kind of funny because there was no like even like Josh said, like all this LLM focus is not what we're going to talk about. So it was kind of funny that way. Like there was some like I don't know if it was like uh, I don't know if there was like presentational pressure to talk about synergies, talk about how you're going to fit with LLMs. I don't really know, but there wasn't anything that I could really add to about that. But it's kind of interesting, for better or worse.
Maybe they had to do it like to attract people to the session, and then well, we got to it in with the LLMs. Now we will talk about something boring. I mean, it's just it's not boring, of course, but it's just kind of like that's the way. No, so that's great. So yeah, thank you for that overview of CBMM, and I'm sure that we can go back over this and think about it some more, and maybe it'll guide some of the things that we'll be doing in the future. Definitely, it's good to get in touch with other people doing things. We do things oftentimes in our own silo, in the sense that we have our own way of talking about it. Yeah. So yeah, so we did have Jesse and I had an administrative meeting this week, and we talked about some things, going forward, some new sort of formulations to projects and new ways we might be doing things. We talked about some of the topical shifts that have happened in the last year, and that's normal for a research group. Um, we also talked about some of the challenges of getting new people into the group, some of the challenges of synergizing, or sort of kind of bringing things together from all of our different things that we talk about. So, we have all these themes that we kind of hit on, and like, how do you bring that into a coherent research theme, into some coherent papers or presentations or whatnot. So these are all things that we need to work on. I think as a larger group. Um, I might go back over that meeting next week. I might bring up some points. We might talk about that. in terms of how we want to approach things, how we might recalibrate. Jesse has talked about his sort of overarching interest in what he called human studies, or maybe it's kind of like a science of learning and intelligence. I'm not sure. He's got a number of different things under that umbrella that he'd like to explore. So that's something that is forthcoming. We're always kind of, evolving our projects and getting new things into place, and discarding maybe things that were not as descriptive or didn't pan out. So this is not a unusual thing. This happens all the time, and I don't expect for Jesse things to be as polished as like the MIT quest for intelligence. Not at all. I just want, and this holds true for anyone in the lab. If you have like some ideas you'd like to pursue, don't worry about how polished they are. Just try to get them out there, try to get some feedback, and try to build on them. What kinds of things might work, what kinds of things don't work, what kinds of things. Don't worry about like someone else setting your agenda for you. It's good to check in with other people's agendas, but your own agenda is your own agenda. Ultimately, that's what you're going to be spending all your time on and pursuing. And you want to create new knowledge. You don't want to just copy what other people have done. So I think with that said, I think that's a good sort of framework going forward. How do we want to what is our flavor of this sort of stuff? And then going back to the CBMM discussion, they talked about like how academic type groups, or basically non-tech company groups, non-industry lab groups, can engage with AI. And they talked about, like a meta theory of learning or other types of theoretical frameworks, not necessarily optimization and things like that, but things that really kind of tie things together that are being worked on in the tech company labs or large labs that are, well funded. And so, that's something that I've tried to steer us into that direction. But yeah, we need to really kind of, I think, stake our own claim on that a little bit more aggressively. It would be nice to see that happen. So that's, I guess that's enough about that. Let's see. Yeah, let me go on to the BICA, discussing BICA. So this week I've had the opportunity, or it was yesterday and today, I think, well, see, it's happening in China, and China's 13 hours ahead of us. So it's kind of like it started Thursday night, which was Friday in China, and then it's continuing on to, I think, tomorrow, or maybe today. I think it's Sunday. It's going to be, this evening is going to be Sunday in China, and I think that's the last day of the conference. So I'm confused sometimes about my terminology, or is confused with like confusing one day with the other, but it's just because we're 13 hours behind the event. So I'm going to share my screen and talk about this. It's a very interesting set of talks, very interesting conference. They're doing a pretty good job of producing it on Zoom. So this is something that's happening in Ningbo, China, live. People are there at the conference. And then there are people on Zoom who are doing it virtually, that they have this hybrid format. And so let me get into the files here. So this is the BICA AI. So this is the site in China where the conference is being held. They're doing, there are a lot of talks on this biologically inspired cognitive architectures approach. So what that means is that they're biologically inspired, and like some of the talks are not biologically inspired, but they do focus on cognitive architectures. And some are more biologically inspired than others. But the whole point is to have, I guess when they say biologically inspired, they mean something that is relevant to neuroscience or cognitive neuroscience or cognitive science. So something you'd find in a biological organism. So for example, if you have a standard neural network, it's just a kind of a network with weights, and there's no physiology, there's no, cognition technique. I mean, it does do things that resemble cognition, but there's nothing that looks like a biological brain. And so this is what they're kind of the point of this whole thing is to talk about this sort of approach. And so this was we had speakers here live, we had speakers virtually. This is, of course, the poster again. And so we've had a number of different people at the conference, a number of big names. John Laird, who does a lot of work with the SOAR cognitive architecture, and he's done a lot of work with some of these other cognitive architectures. So cognitive architecture is where you have different parts of cognition represented in a computational model, and then you have a computational model that can produce outputs. Usually they use them in things like task completion or training. And so there were a number of cognitive architectures mentioned at the conference that I don't think we talk about enough because they're really interesting devices. They have a certain level of representation that's much greater than like a standard neural network. So, for example, you have, things like symbolic representations. There was a lot of talk about neurosymbolic systems, which is like the integration of neural networks and cognitive architectures. And so in that sense, you have two levels of representation at least. There was a lot of talk actually at BICA. A couple of people talked about integrating large language models with cognitive architectures. So you have these tools that are being produced by the tech companies and then integrating them with a cognitive architecture. So, we're at the point now with large language models that you can get models that fit onto a large, something like a Mac Silicon machine. And you can, it's a pain to get it to run, and it takes up a lot of memory because you have to have the weights, and they're usually maybe 30 they're probably about 100 gigabytes, to get the whole model trained, get the whole training set and put it into the model. And then on top of that, you're running a cognitive architecture, which does a lot of these different aspects of cognition or simulates a bunch of these different aspects of cognition. And so then the idea is that that's more powerful than just the LLM. And the same could hold true for maybe like a generative AI model, where you could run something like Midjourney, and you could have like a cognitive architecture on top of that. So John Laird runs the Center for Integrated Cognition. This is at the University of Michigan. And like I said, John Laird originally developed the SOAR cognitive architecture. So I don't know if they have a link to the SOAR cognitive architecture, but here's the cognitive architecture stub here. So this is the SOAR, this is the website SOAR EECS at UMich. So this is a nice screenshot, I think, of SOAR. Let me zoom in. We can talk about it a little bit. So this has been around since like the 80s. And the idea behind SOAR is that it has multiple representations of knowledge. So you have symbolic representations, spatial representations, visual representations. You also have different types of memories. So procedural memory, semantic memory, episodic memory. So episodic memory is where you have specific scenes that are encoded in memory or specific events. Whereas procedural is something where if you have certain procedures like riding a bike or climbing a tree, and you have those procedures encoded in your memory, they're sort of they're not something that you can practice doing it, but it's like something that you can't really describe. When you ride a bike, once you learn how to ride a bike, it's pretty effortless after that. We've talked about that with respect to some of the things in phenomenology, actually. So that's if you've been part of that conversation, you kind of get a sense of what we were talking about. And then there's of course declarative memory, which I guess is similar to semantic memory, where you can you can recite things, and when you recite things, you're recalling something from memory. So it's like specific words or specific episodes. Well, episodic is maybe more episodic memory, but the point is that there are these different types of memory that you can encode into a model. And then there are these multiple learning mechanisms. So you have chunking, which is where you take a bunch of things in the world, like discrete objects, and you learn them as a group of things. It's good for like short-term memory and holding things there in short-term memory, associating things in a group. There's reinforcement learning, which is, of course, this behavioral reinforcement. So if you get rewarded with a piece of cheese or with $5, you're likely to do that behavior again. And so that's reinforcement learning. And then episodic learning, which is where you have an episode of, you learn from episodes. So you learn from experience and discrete episodes. So this doesn't include everything in learning. It doesn't include everything in memory. It doesn't include every type of knowledge, but it does give you multiple options for it. And so if we look at the architecture, this is what it looks like. And notice that there isn't really an explicit reference to the brain. It's a reference to cognition, certainly. We're taking things from, like, I guess in neuroscience, we've studied the different aspects of learning and memory, the different aspects of representation, and that's what's represented here. So you would plug maybe like a large language model into this, and you'd have these different modules that would process information differently depending on what areas of the model were engaged. So, if you had something in like motor learning, which is where you learn something like martial arts, or you learn how to ride a bike, that would plug into this procedural learning module. Plugging that information into the episodic learning module would not be, it wouldn't necessarily be efficient or appropriate. But, if you think about a standard neural network, that might also hold true. If you plug different types of data into a neural network, typically we get, at least for benchmarks, we get pretty good performance. But if we were to plug things in like different types of behaviors, like, procedural learning, and then, try to do something like other types of learning, like scene learning, we might get a very different answer, or it might have a different level of performance. And so, and there are also people talking about robotics at the conference, as well as cognitive models. So, we have this further aspect of robotics. So, there have been a lot of robots that have been developed that have learned how to walk, or learned how to sort of, do things like, different types of movements. And some of those have been based on, heavy levels of artificial intelligence, but some of them have not. So, like a lot of the stuff that Boston Dynamics is doing is really from the passive dynamic walking literature, where they just develop things from a pendulum, a physical pendulum. And they can get, a lot of dynamics out of just that. There isn't a lot that you need in terms of a cognitive model or any sort of neural model. So, there are ways to do things that don't rely on the brain, but there are also a lot of things that you can produce that look intelligent, that don't rely on any sort of cognition either. So, and I say that to contrast it with CBMM, and that CBMM, they're talking about very specific types of models, a very specific view on intelligence. And here we have a different view of intelligence. We have these cognitive models. We have other types of things you can do that are biologically inspired, that don't necessarily involve, that aren't model heavy, I guess is the thing. And notice in the SOAR model here, if you look at this, there is this module for embodiment, and it sits at the bottom, and it's kind of like we have other perception, visual perception, motor. Motor is going down into embodiment. Visual and other perception is coming up from it, but it's just this box. And so it's an interesting take, because that's what I feel kind of like. A lot of times people will say embodiment almost as lip service or as some sort of, you know, I'm going to put embodiment in my model, embodiment box, like it's a separate thing. When in fact, this whole model is in a body that is interacting with the environment. So, the inputs of embodiment can be quite rich. That's not really represented here. It's just kind of like embodiment. What the effects are of embodiment are also not clear. So that's a little bit about the SOAR architecture. Then there's the SPAUN architecture, which is the Semantic Pointer Architecture Unified Network. And this is the acronym SPAUN. This is a cognitive architecture pioneered by Chris Elias-Smith. So Chris Elias-Smith was not at BICA, but he's done a lot of work on cognitive architectures, and especially biologically salient cognitive architectures, in that they use a lot of spiking models. They use a lot of models that map to different parts of the brain. So in this case, this is a model that has 2.5 million simulated neurons organized into subsystems that resemble specific brain regions, such as the prefrontal cortex, basal ganglia, and thalamus. And so the basal ganglia is important in movement and motor control. The thalamus is important for control, sort of as the thing that projects into cortex. And then prefrontal cortex is important in what they call executive control, or some people say higher level cognition, which I hate, because higher level implies that it's, this higher level. It's just bad terminology in my opinion. But anyways, so this type of model can recognize numbers, remember them, figure out numeric sequences, and even write them down with a robotic arm. And this is implemented using Nengo, which is the neural engineering object language. So this is a language that, so it's a graphical and scripting software for simulating large-scale neural systems. So this is actually something that was developed as a MATLAB script, and then it became its own language. So that's kind of interesting. That's how you implement this. Now, this is the source code. Oh, cool. It's on GitHub if you're interested. So this is the GitHub repository here. And this kind of talks about a couple of contributors, talks about how to implement it on your own. There's been a fair amount of hype around it. We'll talk about this in a little bit too later. I'll go to CLARION. So CLARION is the third cognitive architecture I'm going to talk about. So CLARION is this, again, acronym, connectionist learning with adaptive rule induction online. So this is a computational cognitive architecture, has been used to simulate many domains and tasks in cognitive psychology and social psychology, and as well as implementing intelligence systems in artificial intelligence applications. The important feature of CLARION is the distinction between implicit and explicit processes. So this was actually Ron Sun, who we've talked about a lot in this group. He was at BICA, and this is his cognitive architecture. So Ron Sun has been working on this for 30 years. So if we look at this, it's an integrative cognitive architecture. He talked a lot about implicit and explicit processes. They call this the dual process model. So this is out of cognitive science, and has a very good, rich history in cognitive science. You have, different components here. So again, we have these boxes that have, action-centered explicit representation, or goal structure, or drives, or goal setting, reinforcement. So these aren't like connectionist networks necessarily. These are like boxes with like some level of organization. So goal setting might be a set of rules that you implement. And you say, these are my goals, or this is how I set my goals. There might be drives, it's a description. So these are all things that are implemented not as networks necessarily, but as rules, or maybe it could be a network, but it's implemented in a way different from, like, say, like a just sticking a bunch of neural networks together or partitioning a bunch of neural networks. And so this kind of talks about dual representation in the brain, implicit memory and implicit learning, and procedural memory and declarative memory. So these are things that, again, if you're doing your motor learning, if you're learning like a martial art or how to ride a bike, that's something you learn from like the movements of your body. You can train on specific movements, but putting it all together is rather automatic. Whereas declarative and procedural memory are where you learn how to maybe do a task and you can break it down into parts and you can recite the parts, and it's very conscious. So those are the differences there. And so that's the way he thinks of uh, this sort of dual representation structure, and kind of goes, it follows from the cognitive architecture. We had a comment in the chat. So Jesse had a bunch of things here. Let's see. There was a definite bubble around some of the discussion. Yeah, I mean that's true. I mean, groups always have their own perspective on things. Were these cognitive architectures listed at a specific part of the event, or just ones you pulled from it yourself? Well, this is something that different people mentioned again and again. So I'm just giving a sampling of the different cognitive architectures. So, for example, in Ron Sun's talk, he talked about CLARION. Uh, the Chris Eliasmith model was mentioned. Yeah, okay. And then, so they would come up in the talks. They probably should have like a little tutorial on cognitive architectures. I don't know, because I think there's you know room for that, definitely. It's not something that everyone is familiar with necessarily. I think if you're in that community, you kind of know, but going through them all is, I think, because you can bring them into the sort of the present. A lot of these cognitive architectures have been, developed along. They're long-term projects, and so yeah. So Jesse says, I feel like I should do a survey of computational cognitive models project update with these actual architectures. Well, it'd certainly be something if you talked about, maybe models of intelligence. That might be a way to do it because they're very different from like a large language model or like a neural network. And we think of those as models of intelligence. So cognitive architecture might be something worth talking about as well in terms of like what those boxes mean. So the boxes are just like, categories, conceptual categories. Sometimes they drill down into the boxes and they open them up and they find that there are rule sets in there. Or they find out that there may be small networks, or sometimes they're, maybe symbolic, large dictionaries of symbolic terms, like, this thing maps to this symbol, this thing maps to this symbol, that sort of thing. So, they can be implemented in a lot of ways. But yeah, there was a lot of talk about integrating cognitive models with like LLMs and with neural networks. So people are thinking about this a lot. And certainly I think what a lot of the large labs are doing, the corporate labs and so forth, are they're bringing these tools to people to use. And now it's like people can use them to really kind of tackle some of these fine-grained issues. Because, you're going to have a large language model. It's going to have a lot of capacity, but it's still pretty rough in terms of, using it for a specific language or a specific purpose. And so that, and then linking it into something that's actually like going to do some sort of something that resembles cognition. Not now, but maybe next time we might need to review GPT-4V Vision. Yeah, I think that would be good if we could spend some time reviewing some of these models and looking under the hood and seeing what they look like or what they might be useful for. Okay, so one of the reasons why I'm attending BICA is because I have a talk which I did some work with Ankit Grover on, and Ankit basically suggested some directions for, linking this to AI, deep learning, machine learning, and that sort of thing. This talk is on super performers. So the title is Super Performance. Let me zoom in. The title is Super Performance, Sampling, Planning, and Ecological Information. And so I have a 15-minute talk on that up on the YouTube channel for the lab. And then I also have this poster presentation in the form of a poster, and I did this in immersed in VR. So it's, I have like a room around me, and I'm using that actually as a reference point and go through the poster, which you can download separately. It's not really that visible in the presentation, but you'll see if you download the poster. It's hard to do these kind of poster sessions in virtually, and this is one way to do it. They also had a poster session at the conference, but it was in Mozilla Hubs, which is where you create a room and you put a PDF poster up on the wall, and so it's there are different ways you can do that. In any case, I'm giving that talk this evening, so that'll be fun. And I think I don't know if I've gone over that talk or not in the main group. I might give the talk in the main group as well if we're interested. But it's basically about how, in different organisms, in different species, you have sensory sampling rates that vary widely from, humans who sample their visual world at like about 20 hertz to insects that sample their visual world from like 60 to 250 hertz. So that's a huge discrepancy in terms of getting visual information from the world. And so, if they're in some sort of rivalry, and I use the example of swatting a fly, and how humans can not necessarily do that well. And so it's because there's this mismatch of information. You have more planning capabilities than the fly, but the fly has a higher level of sensory input, or at least a higher rate of sensory input. And so that I talk about that mismatch. I talk about like of co-evolving agents that might use different strategies of information sampling, and I get into some things about Gibsonian information and other types of things about information in there that are interesting, I think, broadly to the group. So check those videos out if you're interested. Okay. So then there was this talk by Angelo Cangelosi, and he's a professor of machine learning and robotics in England, Manchester. And he talked about developmental robotics. So he's done a lot of stuff with different types of developmental robotics, implementing them. So it's a little bit different from the cognitive architectures. This is going more into developmental robotics. And so he talked a lot about like merging developmental psychology with robotics and with computational models. And so we'll kind of talk about this in a bit. I have a bunch of papers that I'll kind of go through, and I'll make that paper repository open to people, but one of his papers are in there. We have the papers for the conference too. So if you're interested, let me know. Okay, so let's go back to the papers. So there are a lot of papers here. So this is on the SOAR paper. So this is John Laird, who gave a talk. He's the person who sort of developed the SOAR architecture. And then there's Alan Newell, who was an editor, who is also, of course, well known in AI circles. Paul Rosenblum as well. And they had this from 1990. This is the SOAR papers, research on integrated intelligence. So, we talk about integrating intelligence, but people have been doing this for years. And so this is from 1990. And the SOAR project is an attempt to develop and apply a unified theory of natural and artificial intelligence. At the core of this effort is an investigation into the architecture. So when they say architecture, they mean the fixed base of tightly coupled mechanisms. and that architecture underlies intelligent behavior. So I guess it generates intelligent behavior. You have this thing that's sort of fixed, which is these tightly coupled mechanisms. So, for example, you might have three modules. You might have a input module, which is like the visual system, where it captures information from the environment. You might have a processing system, which turns that into symbols or maps that into symbols. And then you have an output, which produces a behavior that is, can sort of recognize inputs. And so that architecture then are these three modules, and they're all tightly coupled. They can't be decoupled selectively, or else the system won't work. So that's architecture. And of course, architectures are more flexible than that. You can have different types of inputs for different contexts. As you saw from the cognitive architectures, you have different types of memory, different types of attention, and so forth. So yeah, this actually started in 1983, so even earlier in 1990. And so this just kind of goes over the basics. I mean, there wasn't much going on then compared to now, but this book, Unified Theories of Cognition, is something that I don't know if people can get their hands on it, but this kind of gets into SOAR as a model of human cognition. So this was actually something that was printed in 1990. Alan Newell was the main author on it. So there's also this book, Universal Subgoaling and Chunking, the Automatic Generation and Learning of Goal Hierarchies. This was something in 1986. This is something that was sort of the precursor to SOAR. So they say subgoaling and chunking. So this is a very cognitive science, or traditional cognitive science, even cognitive psychology view of intelligence, where you're doing these goals and sub goals and routines, and then you're doing this chunking, which is taking information and putting it into categories or groups and using that as sort of short-term memory, and then encoding that into long-term memory and then recalling it later. So we want to do, we ultimately want to get to these goal-oriented systems, but, we get there in different ways. So this is a nice overview of SOAR, but it's from the early days of SOAR. So that's there. And then we had a lot of other things. This is the Chris Elias-Smith model. So Chris Elias-Smith has published a lot of things in like neuro-inspired computation, computational neuroscience, things like that. This is a paper, a large-scale model of the functioning brain. This describes the SPAUN model that we talked about earlier. So this is this is from 2012. So the SPAUN model is much newer. A central challenge for cognitive and systems neuroscience is to relate the incredibly complex behavior of animals to their equally complex activity of their brains. So this is not focusing so much on human cognition, which is what SOAR was doing, or CLARION was doing, but it's focusing on animal intelligence. So this is where you have different types of animal brains. A lot of them probably are mammalian brains, at least in their conception, but they're going beyond humans. And so it's more flexible in that way. Recently described, large-scale neural models have not bridged this gap between neural activity and biological function. So we're looking at neural activity being like these spiking neurons or spiking neural networks. And you can build one and you can get outputs, right? You can have like a spiking system and you can count spikes and you can say they're spikes. But then, what does that mean in terms of biological function? I guess by extension, cognition. So that's one view of this. This is a very different view from like maybe CBMM or maybe even the SOAR model. And in this work, we present a 2.5 million neuron model of the brain called SPAUN that bridges this gap by exhibiting many different behaviors. So it has a very diverse set of behaviors. It's 2.5 million neurons that can do this. This model is presented only with visual image sequences, and it draws all its responses with a physically modeled arm. So they map the outputs of SPAUN to a modeled arm. So, the SPAUN, I showed you the repository there on GitHub. You could use that uh, software to drive like a drone or an arm or something else, just a very simple output. And you can train it on different inputs. So, you might have a sensor or a sensor suite, might have a camera, and get the input data and kind of make this sort of 3 module system. You have the inputs, the processing with SPAUN, and then the output with some device. It could be an arm, it could be a drone, or whatever. Although simplified, the model captures many aspects of neuroanatomy, neurophysiology, and psychological behavior, which we demonstrate via 8 diverse tasks. So here are the tasks here in the paper. So A0, the 8 tasks turned A0 to A7. A0 is copy drawing. Given a randomly chosen handwritten digit, SPAUN should produce the same digit written in the same style as the handwriting. So it's like the MNIST data set, basically. Oops, this is the Ningo. That's not what I want. Okay. And so you can view the movies online. Then there's image reconstruction, A1. Given a randomly chosen handwritten digit, SPAUN should produce the same digit written in its default writing. So this is not producing the same style. It's producing the written in its default writing, so it's image recognition versus actual drawing. So it's recognizing the image versus reproducing the image. A2 is RL. SPAUN should perform a 3-armed bandit task, in which it must determine which of the 3 possible choices generates the greatest stochastically generated reward. So it's this reinforcement learning. Reward contingencies can change from trial to trial. So the 3-armed bandit is where you have 3 choices, and a bandit is usually like it's like a slot machine. You think about like pulling the lever on a slot machine and getting the trying to get 3 apples. So it's a stochastic process, and sometimes you win and sometimes you don't. And in this case, you have 3 choices, so you can pull all the levers of the 3 slot machines and see if you have a reward behind it. And so that's how a 3-armed bandit works. You'll sometimes hear the term 1-armed bandit, which is just a single slot machine. But and so this is reinforcement learning. You teach the system how to, which system, which options are sort of optimal and things like that. It just follows the reward though. So it's not like this long-term, it's learning basically rewards in front of it. It's not learning over long periods of time. And then given it a list of any length, SPAUN should reproduce it. That's serial working memory, that's A3. So you have serial working memory where things come into your working memory one at a time. And so you can memorize a list and then SPAUN should reproduce that right away. A4 is counting. Given a starting value and a count value, SPAUN should write the final value. So it's inferring something. That is the sum of the 2 values. A5 is question answering. Given a list of numbers, SPAUN should answer either 1 or 2 possible questions. Number or I, what is in a given position in the list? A P question, or II, given a kind of number, at what position is this number on the list? So it's basically trying to figure out procedures and positions and things like that. Rapid variable creation, A6, given an example of syntactic input-output patterns. So it's like something like 0074 maps to 740024 maps to 24. And then SPAUN should be able to complete a novel pattern given only in a set of inputs. So it's like if you get these tests on like the SAT or the GRE test where they say, complete this pattern of numbers, sequence of numbers. So that's what it's trying to do here. A7 is fluid reasoning. SPAUN should perform a syntactic or semantic reasoning task that is isomorphic to the induction problems from the Raven's progressive matrices test for fluid intelligence. So this is reasoning in real time, I guess. And so that's those are your different types of tasks. And so it's doing all these things. It's doing action selection with a spiking basal ganglia model. So it's using these different parts of the analogs to different parts of the brain, and it's doing things like action selection and working memory and other things like that. There's a motor hierarchy that can map to a simulated arm. So there are different like components of this model that it works particularly with motor control or sometimes visual recognition or other things like that. So these are things that this model does well. So that's about that. And then there were a lot of different topics that came up. So the first is this developmental robotics, and I'll go through a couple of these papers really quickly. I'm not going to do them justice, but I just want us to be aware of these things. So this is Angelo Cangelosi from his CV, not necessarily from the talk. This is a roadmap for developmental robotics, which is an integration of action and language knowledge. And he talks a little bit about his perspective on this. So he takes a developmental psychology perspective on this. So this position paper proposes that the study of embodied cognitive agents, such as humanoid robots, can advance our understanding of the cognitive development of complex sensory motor, linguistic, and social learning skills. This in turn will benefit the design of cognitive robots capable of learning to handle and manipulate objects and tools autonomously, cooperate and communicate with other robots and humans, and adapt their abilities to changing internal, environmental, and social conditions. So there are four key research challenges here. The first is how agents learn and represent compositional actions, which means how do they put things together. Two is how agents learn and represent compositional lexicons. How do they put together language? So their actions and language. Three, the dynamics of social interaction and learning. So it's like how do you interact with other agents, and how do you learn that? So you interact, but you also learn it, so you remember it for next time. And then four, how compositional action and language representations are integrated to bootstrap the cognitive system. So all these different things serve as representations, and they help with cognition. And so that's his approach. They talk about this practical roadmap based on a series of milestones, which provide possible sets of cognitive robotic goals and test scenarios. And so his roadmap, let's see if they have a picture of it here. So this is just a comment on cognition. I don't know if they actually have a diagram of the roadmap. That's what I'm looking for, but I don't see it in here. In any case, the roadmap is basically, they have it kind of listed here. So there are a lot of different milestones here. You have, so there's the social learning milestone, which is the next about 10 years. So I don't remember when this paper came out. This came out a while back. But the point is that they've proposed these different milestones at different time windows. So there's the social learning milestone 4, which is the next 10 years, which is to exploit interactions of prosody, internal motivation, intersubjectivity and pragmatics, and language acquisition, developing the associated architectures. There's the social learning milestone 5, which is the next 15 years. So this is where you have a temporally extended understanding of the social motivations and intentions of other minds. That's like theory of mind stuff. Then there's social learning milestone 6, which is a scale of about 20 plus years, which is a very long-term goal. This would be the development of systems that are capable of social learning and pragmatic organization of interaction related to grammar, language, and behavior in various open-ended scenarios. Then there's the cognitive integration milestone, which is the next 2 years, say. This explicitly refers to the development of robotics, cognitive models able to integrate basic action and naming of representations into emergence, shared representation roles for both actions and names, implicitly integrating the capabilities discussed in the previous set of milestones. So it's basically like a base cognitive architecture. There's cognitive integration milestone 2, which is the next 4 years, which is kind of simulating embodiment. So this is, again, kind of building the cognitive architecture, then simulating embodiment. Then in the next 10 years, there's milestone 4, which is developing general purpose grammatical constructions for the creation of new complex motor and perceptual concepts. Integration milestone 5, the next 15 years, that would be new developments consequent to the acquisition of large lexicons and syntactic capabilities will allow the testing in robotics models and research issues in the embodiment literature. So it's like they're building a cognitive model, they're modeling embodiment, they're allowing these sort of new complex concepts to be constructed, and then they're building it into a robot and then answering some larger scale embodiment questions surrounding embodiment. So that's basically his roadmap. So this was from this paper was published in 2010. So this was, some of these milestones should have been reached by now. And so this is a paper on developmental robotics of language learning, trust, and theory of mind. So you did talk about theory of mind, which is like knowing other minds. This is a common topic in cognitive architectures, in robotics, in social robotics especially. So you're doing things where you have to interact with other individuals, other agents, and they have to know what the other agents are thinking. And that sort of helps with that kind of cognition. So let's read the abstract here. Growing theoretical and experimental research on action and language processing and on number learning and gestures clearly demonstrate the role of embodiment in cognition and language processing. So they're looking at gestures, they're looking at action, which is like movement or moving towards objects, goal-directed movements, and then number learning, which involves counting objects. So counting objects, having that be an ordinal thing, figuring out that, if you have 2 of something, it could be 2 like bananas or 2 apples, or they could be 2 groups of apples or bananas, and making those distinctions. In psychology and neuroscience, this evidence constitutes the basis of embodied cognition, also known as grounded cognition. So they also call it grounded cognition. I heard that term a couple times in the conference talks. So that's an interesting point that, when you have these concepts, they have to be grounded in something. And so sometimes when people refer to embodiment, they're actually referring to grounded cognition, which is where you're grounding concepts in something. In robotics and AI, these studies have important implications for the design of linguistic capabilities and cognitive agents in robots, and have led to the new interdisciplinary approach of developmental robotics. During this talk, we will present examples of developmental robotics models and experimental results from iCub, which is a model that they use, and experiments on pointing gestures and finger counting for number learning. So this is where they're actually using the body to count for number learning. So you're counting on your fingers. There's an ordinality to that. There's a sort of using your fingers to represent numbers on base 10. So that's interesting. That's engaging your embodied hardware with your cognitive model. And then they talk about theory of mind, and it's used for autonomous trust behavior in robots. So let's see, we had a comment in the chat. And this is RE grounding. So this is from a tweet from Michael Levin. Okay, so yeah, check that out. Okay, so let me move on to some of the other. This paper is a different developmental robotics paper, and this is on conceptual development from the perspective of a brain-inspired robotic architecture. This is not, or actually Angelo Cangelosi is on this, but he's not one of the main authors. So Uh, so they're talking about concepts being central to reasoning and intelligent behavior. Uh, to this aim, we devised a method for attaining concepts, which computationally reproduces the steps of inductive thinking strategy of the concept attainment model, or CAM. So initially, the robot is tutor guided through its sociocentric cues to attain concepts and is then tested consistently to use these concepts to solve complex tasks. We demonstrate how the robot uses language to create new categories by abstraction in response to human language directed instructions. Most notably, this work shows that the competence emerges from the robot's ability to understand the concepts, similarly to human understanding. Such understanding was also maintained when concepts were expressed in multilingual lexicalizations, showing the labels represented concepts that allowed the model to adapt to unfamiliar contingencies in which it did not have directly related experiences. So, we talk about experiences being important, but sometimes you don't have experience with things, but yet you can still build like models of those things or definitions of those things. So that's an important thing to think about, like various ways of how agents learn, and how do you want to propose that in a model. So that's really what cognitive modeling is. It's really proposing different ways to learn and then putting that into a model that serves as the mechanisms for learning. And they don't have to be neural in the sense of neurons. They can be conceptual. They can be these boxes with components in them, like could be rules. They could be other things. This work concludes that language is an essential component of conceptual development, which scaffolds the cognitive continuum of a robot from low to high cognitive skills, including its skill to understand. So they're building a robot that starts with a low level of cognitive skill or no cognitive skill and build up to a higher level of cognitive skill. Okay. One other thing they talked about in this conference, they talked about neurosymbolic approaches. And so Ron Sun talked about that. There's some other people who talked about neurosymbolic approaches. They mentioned Gary Marcus a little bit. But Howard Schneider is a Canadian researcher, and he does this stuff with neurosymbolic models. So neurosymbolic models are where we have the neural network models, and we also have the symbolic models, and we kind of bring those together. So this is a brain-inspired cognitive architecture approach to the neurosymbolic gap. So in this paper, we considered a brain-inspired cognitive architecture approach to the neurosymbolic gap, and this is where you have this gap between the neural models and the symbolic models. The difference in the abilities of artificial neural networks, e.g. excellent perception, which means that they can perceive things very well, and symbolic systems, e.g. excellent logic. So symbolic systems can produce logical inferences or reason very well. Can be referred to as the neurosymbolic gap. So you have good perception, good reasoning, but you have to bring those together into a common system. Most attempts to combine properties of neural networks and symbolic systems are hybrid combinations of these different systems. A brain-inspired cognitive architecture, BICA, the Causal Cognitive Architecture 5, or CCA 5, is a non-hybrid system with both connectionist and symbolic properties. This architecture uses spatial navigation maps. So this is what we're using, like these different types of maps. Some of them have been produced in we know from spatial representations in mammals that the medial temporal lobe handles a number of different types of representations, like place maps and grid maps produced by place cells and grid cells. So we have this tight connection between spatial navigation maps, representations, and neural mechanism or cells as the common data structure. So we know that like spatial navigation maps in the brain are a thing that have this kind of connection between like a representational model and single neurons that are encoding information. So we know that that's a good model system to work from. So this architecture uses spatial navigation maps as the common data structure. It requires spatial and temporal binding of inputs, which means that you're binding inputs to specific spatial and temporal contexts, the predictive coding, innate knowledge procedures, and the ability to feedback and reoperate on intermediate results. We show how this BICA approach closes the neurosymbolic gap without the need to overtly combine separate symbolic systems and neural networks. So we actually can close this gap without having to actually build something that looks like a typical neural symbolic hybrid. So you can actually use these kind of spatial navigation maps to get around these challenges and actually build something that is integrated. I mean, if you have a known, well-known system that actually does this, it's good to model from that example. We show how this, so as well, given that the BICA model presented is inspired by the mammalian, and in particular the human brain, so there's a recognition that there's this mammalian bias, and a lot of our AI is mammalian biased. So a lot of our, people sometimes mention in passing that like there's work being done under software or C. elegans or whatever. But most of the stuff that we talk about with intelligence in this literature is going to be mammalian centric and specifically human centric. So it's important to remember that it's, we don't talk about intelligence. We could talk about like insect social intelligence, or we could talk about, intelligence, maybe diverse intelligences, but very exotic forms of intelligence that maybe don't even exist in nature on this planet, but might exist on another planet. But most of our examples usually come from the mammalian or human brain. And it provides insights into the mechanisms at work in cognition and in consciousness, which is just kind of thrown in there at the end like a bomb. But this just kind of goes through some of these artificial neural networks that have these good, exquisite sort of sensory processing abilities. And then, there's no symbolic component. So that's where the symbolic part comes in, and then modeling it on spatial maps. That's how they're doing this. So that's that paper. This is a paper from John Laird's talk, or from John Laird, relevant to his talk, on learning to use episodic memory. So this talks about modeling episodic memory in terms of reinforcement learning. So again, you're modeling different types of memory. It's a cognitive concept using an AI type of approach. It's different from what people just employing reinforcement learning on its own are doing. They're just trying to get this reward structure worked out and then use that reward structure to enable very immediate learning goals. And in this case, we're using episodic memory, which is not usually associated with reinforcement learning, but nevertheless is what they're doing in this paper. Then there's this concept that came up. There was one talk where they were talking about they were modeling ideologies and beliefs and, trying to model that in a cognitive architecture. And this is a term that came up called epistemic planning. And so the journal Artificial Intelligence has it's a newer issue. It's from this year. And they talk about this concept, epistemic planning. There's a special issue on epistemic planning. So this is, I think, a really cool sort of concept. The abstract reads, epistemic planning is the enrichment of automated planning with epistemic notions such as knowledge and belief. In general, single-agent epistemic planning considers the following problem. Given an agent's current state of knowledge and a desirable state of knowledge, how does it get from one to the other? So if it gets from where it is now to something that they want to do, it's a very goal-directed approach. You go from one state of knowledge to another, but you move in a goal-directed manner. How do you get there, though? What does it mean to be goal-directed? How do you do that? How do you enable that? And in a multi-agent epistemic planning, the current and desirable states of knowledge Might also refer to the states of knowledge of other agents, including higher order knowledge, like ensuring that agent A doesn't get to know that agent B knows P. Single agent epistemic planning is of central importance in settings where agents need to be able to reason about their own lack of knowledge and make plans of how to achieve the required knowledge. Multi-agent epistemic planning is essential for coordination and collaboration among multiple agents, so it sits as a contrast to theory of mind approaches, where you have an explicit model of your fellow agents thinking, or you try to infer what they're thinking. In this case, you don't know what the other agent knows. So there's this epistemic planning aspect that goes on. Multi-agent epistemic planning is essential for coordination, collaboration, where success can only be expected if agents are able to reason about the knowledge, uncertainty, and capabilities of other agents. It is a relatively recent area of research involving several sub-areas of artificial intelligence, such as automated planning, decision theoretic planning, epistemic logic, strategic reasoning, and knowledge representation and reasoning. This is applicable to a large range of things. In order to achieve formalisms and systems for epistemic planning that are both expressive and practically efficient. So expressive just means that you can use it in a large number of contexts. This is a term that they use in algorithm, designing algorithms. Is the algorithm expressive or not? Can it produce a large number of solutions, or is it very restricted? And this is a topic I think we should talk more about, because this is an interesting way to think about like some of these AI approaches. Last year at the Learning on Graphs conference, which is a conference on graph neural networks, that was one of their major topics, was expressive algorithms. So epistemic planning is both expressive and practically efficient. It is necessary to combine state-of-the-art from several such sub-areas of artificial intelligence that have been so far been considered mostly in separation. So there are a lot of areas for applications to epistemic planning, and they talk about a number of things in the special issue. So it's a really interesting topic. I might come back to that later. There was also talk about the Fitzhugh-Nagumo model. And the Fitzhugh-Nagumo model is a model of excitable cells. So you have these cell assemblies that are excitable, like neurons. They're, they turn on and off. And one interesting thing about the Fitzhugh-Nagumo model is you can not only use it to model neuroscience type problems, but you can also use it to model firefly synchronization. And so it's just a set of agents or set of cells or whatever that are excitable. They turn on and off with the firefly. It's excited, turning on that sac of luciferin in their tail, and they glow, and then they synchronize that activity. And then for neurons, it's where you have, synchronized neural activity, synchronized spiking. And so the Fitzhugh-Nagumo model was brought up, and they talked a little bit about, some of the dynamics of it and how you simulate it. So this is a classical model in neuroscience, and it's, it can be incorporated into a cognitive model as sort of the layer that is not just like, it's sort of like a neural network, except it's very different. It generates very different dynamics. Okay. This is the standard model of mind from John Laird, and they're talking about a common computational framework across artificial intelligence, cognitive science, neuroscience, and robotics. So this talks about theory of mind in terms of cognitive architectures and robotics. This is from AI Magazine. This is a paper from Christian Hook, who also gave a presentation. This is called a neurocognitive architecture. So this goes through some of the sort of, it's a review of cognitive architectures. As the mind emerges from the behavior of the brain, neuropsychological methods are another method to study the mind. Though is a rather indirect method. A cognitive architecture that is implemented in spiking neurons is a method of studying the mind that uses logical evidence directly. A neurocognitive architecture based on rule systems and associative memory can be readily implemented and would provide a good bridge between standard cognitive architectures such as SOAR and neuropsychology. So what they're trying to do here is they're trying to take neuropsychological evidence, map it to some sort of neurocognitive architecture using a standard cognitive architecture. And, they're kind of reviewing this area and how those things can be useful. So this architecture could be implemented in spiking neurons and made available via the Human Brain Project, which provides a good collaborative environment. The architecture could be readily extended to use spiking neurons for subsystems such as spatial reasoning, so you can have subsystems that do specific types of cognition. And could evolve over time towards a complete architecture. So you can start with different modules and you can build up to full cognition, whatever that is. It could be a host of different abilities. It could be a global type of cognition, whatever. Simplifying assumptions made explicit, such as those behind rule-based systems, could gradually be replaced by more neurophysiologically accurate behavior. So these models can be refined in the direction of neurological or neural completeness, I guess you could say. So yeah, this just goes over this type of architecture and talking about how to implement it. This is a paper from the proceedings. This is called Neuropunk Revolution. So this is, I thought Jesse might enjoy this. This is Neuropunk Revolution identifies a set of technologies based on the idea to use neuromorphic computing devices to compensate the pathological work of a patient's nervous system. In this paper, I present approaches for the distributed architecture of implants infrastructure and further results of this revolution. First, I present on one of the possible solutions for the bypass problem to process the inbound data from the motor cortex of paralyzed patients by the thalamus, brainstem, and spinal cord models to orchestrate a spinal cord muscle simulation, taking into account the feedback loop that exists in the biological case. Second, I present the digital components interface to speak the language of the nervous system for the implementation of the neurointerface with real-time simulation for spasticity compensation via the antagonist muscle nerve stimulation. Thirdly, I present the memristive implementation of the self-organizing reservoir computing spiking neural network. So this is a reservoir computer replicating the walking pattern recovery of a rat after complete spinal cord injury. So that's a really interesting paper. They use an interesting terminology for that. This is a paper by Ron Sun on the potential for full human-machine symbiosis through truly intelligent cognitive systems. He talks about this idea of human-machine symbiosis, which has been with us since Licklider, the 1960s, and kind of getting at this synergy using the CLARION architecture, which we talked about earlier. And then finally, there's this paper, Angelo Cangelosi and Domenico Parisi, on the emergence of language in an evolving population of neural networks. This is from Connection Science. And so this talks about, this is actually from the 1990s. So the evolution of language implies the parallel evolution of an ability to respond appropriately to signals, which is language understanding, and an ability to produce the appropriate signals in the appropriate circumstances, which is language production. Language understanding being a more cognitive thing, and language production being maybe a motor behavior. When linguistic signals are produced to inform other individuals, individuals that respond appropriately to these signals may increase their reproductive chances. But it is less clear what the reproductive advantage is for the language producers. We present simulations in which populations of neural networks living in an environment evolve a simple language with an informative function. So they evolve language from neural networks. There's advantages to producing languages versus understanding language. Signals are produced to help other individuals categorize edible and poisonous mushrooms in order to decide whether to approach or avoid encountered mushrooms. Language production, while not under direct evolutionary pressure, evolves as a byproduct of the independently evolving perceptual ability to categorize mushrooms. So they use mushroom categorization as a means to look at how language, the sort of the selection pressures for language production and language understanding. Is it good enough just to produce something that's language-like to communicate this? Or do you need to really understand the language? And this actually goes back to the LLM stuff, because in LLMs, we often have this debate about whether LLMs truly understand what's going on in the world versus just reproducing words. This paper then, this is actually the last one that I had in the folder. This is the development of the conceptual model of creation of an intelligent system. This kind of goes through some of this. Yeah, I'm not going to get into this paper, but that's also in the folder. So, yeah, that was my whirlwind tour of BICA 2023. I had a lot of interesting talks, a lot of interesting topics. I'll make these papers available. I'll put them in a folder and I'll make them available to people to look at. And then the proceedings will be out soon, so there'll be a lot of papers in the proceedings that come from the talks. Any questions or comments?
Yeah, thank you for doing. I'm not going to say much in person in the audio because the delay is still there. But I'll say I appreciate that, and I think I'm going to try to find some different ways to think about or organize it. If you, I don't know if you're going to do it right about the event or not, but I appreciate the exposure to much of the cognitive architectures that I feel like I kind of, I don't know, Beacon every year is something that I like only tangentially observe or participate in, but there's a lot of things there. A lot of the runs on and Angelo, whoever, like those things are really on point. So I need to go in that space and figure out some things. But yeah, thank you for that.
Yeah, no problem. And thank you, Morgan. Yeah, it's good. I'll do a write up on this later. So yeah, that's good. We had, they're very familiar faces. So yeah, so we had the MIT perspective or the Boston perspective, and then we had the BICA perspective. And I think it's really good to have like all these different ways of doing things. And I think the open questions or the roadmaps are good to like kind of revisit and think about. Okay, well, that's all for this week. Thank you for attending and have a good week.